So, good evening. I will start with sound now. Okay, like you all know, sound is a form of, it's a wave, it's a form of energy transfer from one point to another. You also know that sound is a longitudinal wave. So, waves can be classified as two types, longitudinal and um, transverse waves. Sound is a type of longitudinal wave. Now, when you have sound wave, it progresses as a set of rarefactions and compressions. Now, if you understand, suppose this is a zone or a region where there is a lot of air. So, suppose in this region there is a lot of air, and if you look at the clapping, what you are actually doing is you are physically compressing the sound between two regions. So, between your hands, sound is getting compressed. Now when you are compressing air, here this air has come from its neighboring zones here and here. So here there is a low pressure, here there is a high pressure, and here there is a low pressure. Now in due course of time, the very next second, what happens is, we know that air from a high pressure zone will rush towards a low pressure zone. So the very next second, what happens is the high pressure is generated in this area because the air from the neighboring zone has reached here. So you had a high pressure first, here you had a low pressure, that low pressure becomes a high pressure, next becomes a low pressure, again that low pressure becomes a high pressure, because the surrounding air is coming and occupying that space. So basically what is happening is that sound progresses as a density disturbance, or it progresses as a pressure disturbance, or it progresses as a so there is a density disturbance which is moving, because that region where there is a high pressure will have a high density. There is a pressure variation, pressure disturbance. Alternatively, the gas molecules are also moving, so there is a displacement wave. So a sound wave can be expressed as a density wave, it can be expressed as a pressure wave, or it can be expressed as a displacement wave. So let us try to understand this a little bit better. Now suppose, but whatever it is, ultimately there are compressions and rarefactions, and this is how the sound wave propagates. We can say this is a compression, this represents a rarefaction, again it represents a compression, again it represents a rarefaction. So there is a high pressure, there is a high pressure compression, there is a low pressure rarefaction. So there are crests and troughs. So the sound wave propagates as a series of crests and troughs. Okay, so this is what you need to understand. Now if P varies as P0 sine omega t minus kx. So this is a wave, this is a pressure wave, where I have given the variation of pressure as a function of omega t and kx. That means as x varies, the pressure varies, as time varies for a given x, pressure varies. So this is what is a pressure wave. Now the sound wave can be written as a pressure wave, as a density wave, or as a displacement wave. So I am explaining that when you express it as a pressure wave, you may say P is equal to P0 sine omega t minus kx. When you say it is a density wave, you can say the density is equal to some rho naught into sine omega t minus kx. When it is a displacement wave, you will say it is equal to some s naught into cos omega t minus kx. What you need to understand is that if pressure is very high, automatically density is also very high. But if density is very high, the displacement of the particle is very low, right? So there is a phase difference. At those points where the density is very high, the displacement will be low, and vice versa. So wherever P is max, S will be 0. Wherever P is minimum, again S will be 0. Okay, so you have to understand that there is a relationship between these three. What I will try to do now is I will try to relate all these and then try to see if we can logically find out if one wave is given, how do you get the equation for the rest of the waves. Okay, we can start from anywhere. I will assume a pressure wave is given, P is equal to P0 sine omega t minus kx, and I want to know the density wave. Okay, so now I know that rho is equal to mass upon volume. So from there I know d rho is equal to minus of m upon v squared into dv. I am just differentiating this and finding out that this is what it is. So from here I know that d rho is equal to minus rho into dv by v. This m by v squared can be written now as m by v into dv by v. So dv by v. Okay. Now for a gas, the bulk modulus B is equal to pressure divided by delta V by V. So from there I know that delta V by V is equal to P by B. So if I make this substitution here, I will see that d rho is equal to rho into P by B. Yeah. So now P is given to me as a P0 sine omega t, P0 sine omega t minus kx. So I can write d rho as rho P0 by B into sine of omega t minus kx. So if I have a pressure wave P0 sine omega t minus kx, I want to convert it into a density wave, where density is equal to, where the variation in density d rho is equal to some constant rho naught into sine omega t minus kx. So this rho naught is what is equal to rho into p naught by b. So this is how a density wave can be related to a pressure wave. Okay, so I hope you are able to understand. So if I give you the amplitude, pressure amplitude, you can find out what is the density amplitude. The important point to understand is that if I represent a sine wave like this can be variation of pressure with time, or it can be a variation of pressure with displacement, or I'm sorry, I should have put x here, I should have put t here, I should have put p here. Remember, time is always an independent variable. Similarly, I should have put an x here, I should have put a p here. Or it can be density also, there is no problem, just that the amplitude will be changing. How are they related? That d rho is equal to rho naught sine whatever, that rho naught is equal to density into p naught by b. This is how it is related. Okay, so I hope you are able to understand.